Thank you. Thank you very much for the invitation and for the kind introduction. Um, as mentioned, the topic of my talk will be data anonymization, and data anonymization is a really complex problem. So I try to come up with a slide set that is sort of not too theoretical, not too practical. It talks a little bit about methods, but also about implementations. And I was really happy to see all the great questions that were sent to me before this talk, and I'm also looking forward to the discussion then. So I will basically cover 5 different topics. I will first start to tell you a little bit about the background about data anonymization. There will also be some legal aspects involved, as data anonymization is a topic, and from my perspective, sort of on the intersection of law and technology. And I will then proceed to talk a little bit in more depth about the different threats that data can be posed to, basically, or that it must be protected from sometimes, and different ways of capturing these threats and implementing protection methods. I will then also talk a little bit about the anonymization of the results of analyses, because it's often not only the primary data that needs to be protected from disclosure, from privacy threats, but also, in particular, of course, in the scientific context, results of scientific analyses that might be done in different areas. I will then proceed to also tell you a little bit about ARX, which is a tool that we have developed, or I and my group have developed over the last almost 10 years, which is one of the quite well-known tools in the field for anonymizing structured data. And I will then also go on to show you a few real-world examples where data anonymization has been put into practice, and try to sort of provide you some insights into how this can be done. So background first, I work at the Berlin Institute of Health at Charité, which is a large university medical center in Berlin. And we sort of research and also apply data anonymization in the context of medicine. But it's of course relevant also for other fields. In medicine, there are quite a lot of initiatives also ongoing for almost 10 years now that aim at sharing data across different institutions within countries, but also across different countries, for example, in the European Union, to make things such as precision medicine a reality, where you really try to tailor diagnosis and therapy to the specific characterizations of individual patients or probants or citizens. And to be able to develop such methods, you basically need very large data sets and need high case numbers in order to be able to carve out those detailed characterizations. And also, this often involves the secondary use of healthcare data for research purposes. And these are all areas where data protection and then also anonymization can play an important role to make those research processes a reality in the first place, basically. And of course, there's also this large movement towards open science, also to some degrees in medicine, where the idea is that much more information about scientific projects is to be made available basically to the public in a transparent form. Also, involving often primary research data, or at least in the best case, primary research data that is being used in studies. And there are also funding agencies that are increasingly requiring third-party funded projects to release their data to the public. And of course, also in this context, data protection and data anonymization is quite an important topic in the area of medical research. But of course, it's also important in other domains, in the scientific domain, but of course also in, for example, the commercial domain. So one quite important slide from my perspective is on terminology, because, as I said, there's a lot of complexity involved in data anonymization, and there's actually also a lot of complexity involved in terminology. When people talk to each other about data anonymization, I often have the feeling that they are sort of not really understanding each other, because they are using different terminologies. So here's a slide with a specific focus on the EU General Data Protection Regulation and the terminology that is used. So terminology that is used in the GDPR is, for example, personal data, identified or identifiable person or data, so sort of data that is identified or identifiable, and there's anonymous data, which is sort of the exact opposite of personal data, which is then also not covered by the GDPR anymore. And the term, which is also very frequently mentioned when people talk about the GDPR, pseudonymization. But what is important, which is the terminology that is not used in the regulation. So, for example, what terms that are very often used are de-identification or de-identified. These are terms that, for example, come from US legislation, but they don't really have a meaning in the context of the GDPR. They are not mentioned in the regulation. It's not at all clear what this is supposed to mean. So I would suggest not to use the terms de-identification or de-identified. Another term that is often used is coded, which I think is it also comes from the context of the UK, and is supposed to be somewhat synonymous to the term pseudonymization or pseudonymized, but it's also not mentioned in the regulation. And that is interesting. The terms that are also not mentioned in the regulation are anonymization or anonymized. And the regulation talks about data that has been rendered anonymous. So sort of anonymous is a property of a data set. It's not a property, or it's not a process description. It's not saying that a certain process has happened, but it's a state of data. I will talk about this a little bit more over the next couple of slides. And important to say here that this is, of course, the legal perspective on anonymization in the European context. And when we take a look at the technical technical view in a few minutes, then we will see that there are quite a few differences. And of course, there you might also be aware of that there's a range of principles in the General Data Protection Regulation, such as lawfulness, fairness, transparency, purpose limitation, and so forth. And data anonymization is often seen as a tool, of course, for rendering data anonymous, to have it sort of fall out of the scope of the GDPR. But this is difficult. I will also talk about this. But even if this is not the case, then anonymization can be an important tool to implement other principles that are mentioned in the GDPR. For example, data minimization, which means that you should only process the data items, the amount of data that is actually needed for a certain processing purpose. Anonymization can be a tool to achieve that, but also things such as a storage limitation, for example, and to some degree, confidentiality of data. So what is anonymous data according to the GDPR? And this is also quite interesting because this the term anonymous data is not really defined in the GDPR, but what is defined in the GDPR is personal data. And then sort of anonymous data is defined implicitly by being sort of the opposite of personal data. So it's important what personal data is according to the GDPR, and there we can take a look at, for example, recital 26, which says that the principles of data protection should apply to any information concerning identified or identifiable natural persons. So the question is, what does it mean that somebody is identified or identifiable? And there recital 26 says that we should sort of take into account all means that are reasonably likely to be used to identify a person directly or indirectly. And this already shows that there's sort of that we can make some assumptions when reasoning about the fact whether or not data is personal. And recital 26 then also goes on to list a set of factors or objective factors, examples of objective factors that can be used to reason about the question whether identification or a certain way of identifying individuals is reasonably likely. And there are things such as the cost that would be needed, or the amount of time that would be needed to identify individuals. And also quite interestingly, the GDPR sort of also projects this into the future and says you should consider technology that is available at the current point in time, but also technology that might become available in the future. And this, of course, makes it quite difficult to sort of share non-trivial data sets openly, because once you, for example, put the data on the internet, it's of course, you must consider this sort of to be publicly accessible also in the future, and you don't know how what future developments will come. So this is already a good argument for sort of creating protected environments for sharing data that is supposed to be anonymous, and to not only, and this is interesting, to not only see anonymity necessarily as a state of data, but as a state of data in a certain context. So how reasonably likely is it for data to be re-identified? There's a very, very well-known example there, but there are many more actually in the scientific community working on data anonymization, and that is the re-identification of the governor of Massachusetts, William Weld, in 1997 by LaTanya Sweeney, a PhD student at this time, now a very famous professor working, amongst other things, on data anonymization and data privacy. And what happened at the time, there was sort of a political discussion going on about whether or not data from the Group Insurance Commission in Massachusetts, so basically billing data sets collected at medical centers, could be made publicly available for research purposes. And the governor, William Weld, was one of the people arguing that this is actually a good idea. So because they, of course, planned, or they actually also did this, removed identifying information such as names or addresses of patients from the data set, and then wanted to make it publicly available. And as mentioned, William Weld was one of the people also really being supportive of this idea, and it was actually also implemented. So the Group Insurance Commission published these hospital discharge data sets. And here is sort of an example of the attributes that were in the data set. So things such as the zip code, the date of birth, and the gender or sex of the patients. And in addition to this, some medical data, most importantly, diagnosis, procedures, medication, and also what was charged for this hospital stay. And what then happened is that William Weld actually collapsed during an event that was broadcast live over TV, and it was rushed to the hospital. And then LaTanya Sweeney had the idea, that's quite interesting, because now I know that there must be a record about William Weld in this hospital discharge data set that is being published. So she went on to purchase a voter registration list. This is also something that is not that common, as far as I know, in the European Union. At least it's not possible in Germany, but in the US you can buy the voter registration lists, which contain quite a lot of personal information about registered voters. And there's an example of the attributes contained in the voter registration list here. So there are things such as names and addresses, the party and affiliation when the voter has registered, but also the same attributes, zip code, date of birth, and sex, that are also in the hospital discharge data set. So what Sweeney then did is quite trivial. She basically joined or linked the voter registration list with the hospital discharge data set, and by this process was able to re-identify the medical record of William Weld, and of course to gain insights into the diagnosis, into the procedures, and the treatment process. So this basically is, at least in one of the communities, in particular in the computer science community, sort of the starting point for working on data anonymization technologies. It has to be noted that there are other scientific communities, in particular the statistics community, also in the area of official statistics. So when you're doing census, for example, want to publish census data, have been working on this problem for many more decades, actually, but with this specific focus on population data, which has some, let's say, specific properties. For example, it's typically a random sample of the population, and hospital discharge data is not a random sample of the population. So this was sort of a huge scandal, and the first time where it was really shown that basically anonymizing data is not that easy, and of course that it's not sufficient to just drop directly identifying attributes, things such as social security numbers, names, addresses, these attributes that are highlighted here, but that more needs to be done to a data set, because otherwise you will sort of have unique keys within the data set. The combinations of different attribute values will be uniquely identifying for certain individuals, because their sort of properties that are reflected in the data can become unique quite quickly. And there were lots of follow-up studies. As I said, this whole sort of domain of working on data anonymization techniques, which really has developed hundreds or probably even thousands of different approaches of trying to deal with this problem over the last, this is around 25 years already. This has sort of been started with this famous attack. And there were also, of course, a lot of studies trying to find out how huge the problem really is. And this is what the figure on the right side is showing. There are different estimates. I think this is one of the more strict estimates, but there was a work that basically showed that around 87% of the US population can really be uniquely identified by taking very simple demographic information, a 5-digit zip code, date of birth, and sex. There's a distribution here, and you can see that it, of course, depends a little bit on the age. The older you are, for example, the more unique you become, because there are less people in the population of the same age. And but generally already these three very basic attributes that were also used in the linkage attack by Latanya Sweeney are quite identifying already. And that's actually where the problem starts, because of course a trivial solution would be for these specific attributes to just remove them from a data set. But typically they are also needed for scientific studies. So in the area of data anonymization, you need to deal with exactly this problem. What do I do with data that is needed for a study, that needs to be included in a data set, but at the same time it's potentially identifying? And this actually sort of has been rediscovered in 2019. There was a Nature Communications article that was quite successful, actually also got a very large media coverage, where researchers from the UK and Belgium basically have shown that these types of re-identification attacks are possible also, of course, for higher dimensional data. They did this for up to 15 different demographic attributes and developed a machine learning approach to re-identifying individuals. There's also a website where you can play around with this, but it basically shows the same problem again. And as I have a few examples here in the slides, for example, from the New York Times, really get a very high attention basically to this problem, which also, of course, shows that 25 years later, the problem is not yet really solved. So this is also one of the key takeaway messages. Data anonymization is not generally impossible, but it's a really, really hard problem, and only works in some contexts currently. And there's still ongoing research. There's still a large community trying to sort of solve these types of problems. And of course, this re-identification through demographic data is just one example. There's a range of papers that have shown that this can be done with other data types as well. This is a slide that I adapted from a presentation of Brad Malin, which is also a famous researcher in the field. And here you can see that there are papers that showing that this is problematic for diagnosis codes, of course, for genetic and genomic data, but also for things such as pedigree structure, location data, so location traces or visits are particularly difficult to anonymize. There were also papers that's quite interesting that were able to re-identify people in Netflix movie reviews by linking the Netflix reviews through information from the International Movie Database. There is a lot of work on social networks and social network structures. So this is basically really an endless list, because obviously any non-trivial amount of attributes will basically be able to form unique combinations in a data set and, for example, enable linkage attacks as Latanya Sweeney did it. But in reality, of course, or not of course, but in reality, so maybe let me put this a bit differently. This has brought many people to believe that data anonymization is basically something that just doesn't work, and we basically just shouldn't do it. But in reality, I would argue, and also many other people argue, there's also sort of a divide in the community that this is not actually true, because re-identification or anonymization depends on a lot of factors, right? So if we revisit the attack by LaTanya Sweeney, for example, she knew that when the governor was rushed to the hospital, because she knew the date at which he did this. He was on the TV and had this medical event happening. So there's a lot of background knowledge that was actually involved. And this is true for many of these attacks, that often you need quite a lot of background knowledge to be actually really able to perform these types of attacks. And you might still be left, for example, also with quite a lot of uncertainty about whether or not linkage, for example, that you are doing is correct or not, because the risk of re-identification not only depends on the data set, but it also depends on the relationship of the data set to the population from which the data set was obtained. And so there are actually lots of factors that can influence this. And as long brings me back a little bit to what I said before, that it's probably typically not a good idea to really openly share sensitive data. But if you're able to control the environment in which this is happening, and when you're able to control, at least to some degree, the background knowledge of attackers, or the potential motivation of attackers or recipients of data, then there can be quite a lot of situations where this is actually relatively safe to do. Now, that was a lot of sort of background information on methodological aspects or on legal aspects. So let me also try to bring this sort of in line with the technical perspective on data anonymization. And as sort of my number one example through the remainder of this talk, I will basically use tabular data, so data with quite a lot of structure. But I also know this from the many questions that you sent me. Data anonymization is, of course, also something that is relevant to other data types as well, and I will have a slide on this in a few minutes. But basically what happens when you anonymize data, you sort of have an input data set, and out of this input data set, you generate an output data set. And this output data set is to be rendered anonymous. So at least in the perfect situation, it's really an anonymous data set also in the legal sense. As I mentioned before, might not necessarily be the case, but at least you would, of course, want to have re-identification or de-anonymization or privacy risks to be reduced in the output data set. And there are many different ways, actually, in which input data can be transformed into output data. There is more sort of traditional anonymization techniques, but currently also a very large topic in the research field is synthetic data generation, which can, for example, also be seen as a process of having input data and turning it into some protected output data set. And there's basically actually the same challenges that apply to data synthesization than to traditional anonymization techniques. So this is a very simplified example. I'm sorry that it is in German. It's basically the typical demographic attributes: age, gender, zip code, weight, and diagnosis, encoded by ICD, which is a commonly used terminology in the medical domain, particularly for billing purposes. And of course, a very simplified example, just to sort of give you an insight into the idea. And what is then happening to produce an output data set is here a random sampling step. So we sort of take a random sample of a subset of the records. We apply aggregation in this case to age by replacing certain combination of values, for example, by their mean. And we can do suppression by removing individual values. Here, a few values have been removed from the gender. And there is masking that can be done in this case to the zip code. So we basically drop a few digits from the zip code. At least in Germany, this also works quite well because there's, at least to some degree, a little bit of hierarchical structure encoded in the zip code. And you can do categorization. So here we have categorized the weight. And you can also generalize things. In this case, there's sort of an hierarchical structure behind the ICD diagnosis codes, which we can use to sort of drop some information, in this case, on the localization of certain types of, in this case, cancers. So, and in the end, we have an output data set which now can sort of provide us with more protection. And there are also different ways in which this can be done. There are more like rules of thumbs approaches where you sort of have best practices and transform data a little bit as long as it's still sort of suitable, for example, for the analysis what you want that you plan to do. But there are also more strict approaches where you really have a formal model for measuring and quantifying risks, and maybe also an I'm sorry, maybe also an automated optimization process that turns your input data into an output data set that then fulfills certain guarantees. And in this case, we do have a few guarantees that hold on the output data set. So first of all, this data set fulfills 3 anonymity, which is sort of the most well-known privacy model, very basic, and has actually been proposed by LaTanya Sweeney as a potential way to deal with the attack that she has shown on the governor of Massachusetts. This basically means that that sort of the information of people is hidden in a crowd of people. In this case, each and every record, as you can see, is indistinguishable from at least 2 others. So it's 3 anonymity groups of at least three indistinguishable individuals in the data set, 3 up here and 3 down here. But also this model, if this is implemented in a randomized manner, or with this transformation is done in a data-independent manner, then this process of transforming the data set actually also fulfills a model called differential privacy, which is sort of by many seen as the sort of gold standard nowadays in data anonymization, or generally in privacy-preserving data processing. But also, of course, at the same time, we see that that there's an inherent trade-off of protecting data against risks, and at the same time maintaining the usefulness or utility of data. Here we have done significant transformation. There's probably quite a lot of statistical bias in the data set that we have generated. And it's, of course, an open question. It's a simplified example, but in this case, it's really an open question whether sort of scientific questions that would be answered on that data set, or whether the results would really be valid, or more likely significantly differ from the results that would have been obtained if one had used the input data set for this purpose. And this brings me to another sort of central message in my talk. When you anonymize data, there's basically an inherent trade-off between the utility of output data, so the usefulness, the scientific side, and the degree of protection that you can achieve, which is sort of also the legal side here. And you can plot this on such a sort of abstract graph where we have the degree of protection here on the y-axis and the scientific utility on the x-axis. And there are, of course, a few extreme points. So down here, you would have no protection and no scientific utility. This is, of course, completely uninteresting. And up here, there's an extreme point where you could say you have no risks, perfect protection, but this also means that there is no risks, perfect protection, and basically all data, just handing all data out as it is. But this is unfortunately not achievable because we need to do something to the data to reduce risks. So which means that in the end, there's sort of a curve that we have here, and we have to really take care that we are not too much up here, because when we're up here, then we have a lot of protection, but we're doing sort of bad science because we don't have any scientific validity in the data. And down here, we are basically might be breaking the law if data really needs to be anonymous, basically. But we do have quite a good utility. And when you do have a good transformation method, the graph might look something like this, so that you are really able to significantly reduce risks while not sort of giving up too much usefulness of your data set. But this can sometimes be difficult to achieve or not even possible. And then, of course, what you can also do is, and I mentioned this, or probably also need to do, you can share data sort of in protected environments, which sort of shifts the curve a little bit, right? So this means that you might be able to achieve more protection with doing less modifications to data, which is typically the way to go to sort of have a multi-layered protection approach, and try to sort of control the context in which data is being accessed, to be able to and better manage risks. So, but there are also, even with this abstract perspective, there are a lot of challenges involved, because here on the legal side, we need to ask ourselves, excuse me, how can we sort of quantify this? How can we measure this? And there are questions such as, what is actually personal data? What is identification? I talked about the legal perspective, but if we are anonymizing data, we need to somehow have a sort of a quantitative or qualitative approach to sort of approach this problem. And also, what is an acceptable risk? So let's assume the output is a risk value between 0 and 1. When do we consider a data adequately anonymized? We cannot reduce risks to 0. So we need to have some form of threshold. What is an acceptable threshold? Unfortunately, there is no threshold in the law. And it's the same thing basically on the scientific side, on the utility perspective. We need to sort of be able to estimate or measure, if we, for example, do an automated anonymization process, the utility of data. This is also extremely challenging outside of particular use cases. Of course, when you do know that a particular analysis is to be performed, or the particular attributes that are of interest, then this problem sort of becomes approachable. But it's very hard to approach in case you're sort of looking for a general purpose anonymized data set. This can be really difficult. It can work when you know that there's only very little modifications that are being done to the data, but as soon as modifications become significant, then it's really, really hard to say anything about the utility of a data set. So another important message, somehow also mentioned this a little bit, is that anonymization is a context-specific problem. It's context-specific regarding the recipient, the background knowledge, what the recipient might want to do with the data, but it's also dependent on types of data. And this sort of also fits a little bit to the questions that I got sent beforehand. There were some questions in there about how can I anonymize imaging data, for example. How is it with different types of approaches for anonymizing textual data? And these are really different anonymization techniques that also are differently strict, I would say. There was one question that was exactly mentioning that when we're talking about textual data. So in the medical context, it's typically clinical narratives, it's physicians' letters, stuff like that. So what is typically being done to anonymize these letters is to basically just drop sensitive or identifying tokens or words from data sets. But of course, this is not sufficient, at least not in the context of the GDPR. Typically, to come up with a data set that where you have strong guarantees that it's pretty hard to re-identify individuals, because, for example, you could also just link the text without the tokens to the original text that you have to directly find out which patient a certain letter refers to. And this brings me to another point. That's a very interesting question about whether or not anonymity is sort of seen as an absolute property of data or as a relative property of data. I always mention that you should construct secure environments. You need to control the context in order to be able to even achieve anonymity. And that's definitely my personal opinion and the opinion of many others in the space. And that's also how it's implemented in many countries quite successfully. So, for example, the UK is doing a lot of data anonymization following exactly this idea that anonymity is a relative property. And when you control what can happen to the data, you can make certain assumptions. But when you take a look at the GDPR, you might get the feeling that the understanding of anonymity is actually an absolute understanding, because it clearly says that data needs to be anonymous, not only for some recipients, but actually also for the original data holder. Yeah, and this is basically almost impossible to achieve generally. And that's why I believe it's not a very practicable or actionable perspective on anonymity. But it's definitely something that you will frequently be confronted with when you talk about anonymization with lawyers, for example. So Also, a reason why there's not so much anonymization being done in the context of the European Union, at least from my experience, because there's so much legal uncertainty around it. It's not 100% clear how those different legal requirements need to be interpreted, and whether there are interpretations that are valid that still make anonymization feasible. And this absolute versus relative is one very good example, because I would argue that anonymization, as we understand it, or as I understand it in this talk, is basically not really feasible when you're not able to sort of make assumptions about context. So this may be to text, where it's typically the case that the tokens are being removed, not so much of deriving more formal guarantees as the text about the text itself. And it's the same also with techniques for anonymizing images. For example, in the medical context, there are tools such as MRI deface, which sort of remove the obviously identifying information from certain images. In this case, you can see the face, but it might still be the case that some other parts of the head here, for example, are so unique to a specific person that you could use this information to re-identify, or you could also sort of mask with black rectangles certain parts of images. But of course, this will never be perfect. There are other approaches when it comes to facial images, for example, that try to be a little bit more formal by averaging, for example, the images of different people, to also have sort of follow this idea of hiding individual information in a crowd of certain individuals. But as far as I know, that's not something that has really been successful in practice. And there are other techniques when we take a look at, for example, time series data set, biosignals in medicine, or also even genetic data. There are some approaches. Genetic data, of course, has the problem that there's sort of some inherent identifiability, inherent sensibility of the data. But even there, when you make certain assumptions and construct certain models, they're actually tangible to try to anonymize such data sets, but still the approaches that have been proposed, it's a bit unclear how they would be seen from a legal perspective. Then there's this huge area on analysis results. I also have a few slides on this. How can we sort of protect the results of analysis, which is also not necessarily an easy problem, for example, when it comes to statistical tables. And then there's this whole area of structured tabular data, which is my personal focus, at least in most of my work, and which I will also talk about a little bit more on the next couple of slides. So tool support is also, and I really need to hurry up a little bit, so I think I will just see how far I come. So tool support is also quite an interesting topic in this regard, because there are not so many tools readily available for helping you to anonymize data. As I said, I have a particular perspective on tabular data, and this really has to do with the fact that this is quite complex. So in particular, if you're not focusing on a specific let's say on a specific law, which gives you a very clear definition of anonymization. There are examples of this. So in the US, there are laws, for example, that very specifically describe how data should be anonymized, also referring actually to this attack by Latanya Sweeney and requiring you to sort of remove attributes that are susceptible to such linkage attacks. Then it is relatively easy to develop tools. But if you don't have those very specific requirements, you basically need to sort of create a Swiss Army knife, right? So you need to implement a range of mathematical and statistical models, different ways for quantifying things, different ways for transforming data, because data is always different. And this makes it really, really hard to actually implement such tools. And in the space of tabular data, I can basically recommend you two tools. There's one called SDC Micro with a few related tools, which is basically a package for the R statistics environment. And there's ARX, which is the software that my group is developing. And apart from that, you will find a few more, in particular, of course, open source solutions on the internet, but they are all not very mature. It's more research prototypes that are not very well suited for actual practical applications. So I think I will try to make this a little quick. I have around 50 more minutes. Basically, the message here is that this sort of wanted to give you an insight into this complexity here, right? So we need to measure risks and we need to measure utility, and there have literally been hundreds of different models that have been proposed in the literature to, for example, measure risks. And this has to do with the fact that there are so many risks. And just to give you sort of an example, you can focus on linkage attacks. So really try to find out which combinations of values do make individuals unique. But this is actually not enough. So this is a good slide. Then you're just basically dealing with identity disclosure or record linkage, where someone is really able to link a certain individual to a certain record in a data set. But there might be much more that can go wrong, even if you're not possible to link a record to an individual to one specific record, but let's say maybe to a set of records in a data set. This could still be used to infer sensitive information. So let's assume all those individuals share the same diagnosis, for example. So, or there's a very skewed distribution of the diagnosis within this group of individuals. So this gives you some insights into sensitive values that are associated with a person. And but we could even go one step further and just try to determine whether or not an individual is probably reflected in a data set. There's probably data about this individual contained in the data set. And even this can be hard to protect from, and there's not necessarily needed to really link an individual to a very specific record. It can already be sufficient to be able to link an individual to a set of records with relatively high certainty. So this already gives a sort of an idea of the complexity involved, and then there are different models for dealing with this, and you can also make different assumptions about what the individual, what the attacker wants. This is another well-known model where you can distinguish. Yes, of course.
Just small information. If you need more time for a presentation, it's perfectly okay. You can use more time for the presentation. Thank you very much. Your presentation is very, very interesting. So we don't have any problems with denoting more time for it.
Yes, thank you very much. That's very good to know. But I will still hurry up a little bit. I could talk about this probably for the whole day, but good to know that I don't have to stop in 10 minutes sharp. Thanks. So as I said, this is another example, another well-known model where you can distinguish attackers regarding what they actually want, right? So some attackers, this is called the prosecutor model, are really interested in finding out something about a very specific individual. So the police would be an example. The police is sort of prosecuting someone and trying to obtain additional information about a very specific individual. Then you could say that an attacker is more of in acting more of in a journalist context. So what the journalist basically wants is he or she wants to find out something about any individual. It doesn't really matter which individual it is. You just want to sort of show that it's possible to extract information out of a data set to, for example, make a career out of this. And this is actually really something that has happened in the scientific community. There are quite a lot of people that have become very famous by attacking data sets, by showing that there are vulnerabilities. And there's also something such as a marketer scenario in which you assume an attacker that doesn't really care about a specific individual. The attacker also doesn't really care about whether or not there's a huge certainty associated with the information that is being extracted. Just wants to be the information that is being extracted to be somehow correct on average. So let's assume, and he wants to do this for as many individuals as possible. So let's assume you want to send spam emails, for example, and you try to find out the email addresses of people. You don't really care if 30 or 40% of the email addresses that you selected are actually wrong and don't match to the individuals, as long as you got 30% that are correct. And then you just send out your spam email. So these are just sort of a few of the well-known axes that can be used to somehow distinguish between different types of privacy breaches, different motivations of attackers. And of course, you can make different assumptions about the attributes that an attacker might know. You can make different assumptions about the relationship between the data set and the underlying population. So how large is the population? Has the data been sampled randomly, or is it some form of skewed distribution? It's always good if it is a random sample, but for example, because then you can do interesting things from the statistical perspective to get good risk estimates. But for example, in medicine, it's typically not a random sample of the population, so these methods cannot be used actually. So this would be an example just to give you a little bit more insight, but maybe let's continue with this slide. This is just to show that it's the relationship between actually the attacker's background knowledge. We could also call this the population that is known to the attacker, and the data set that is actually disclosed by taking a specific look, in this case, on re-identification. So let's assume that this is the data set, again, a very, very simplified example, the data set that you are basically publishing. And you can see that there is one unique record within this data set. That's 55 years old, male and white, with a certain cancer. And of course, if you, for example, consider the k-anonymity model, you would assume that there is 100% risk, basically, for this individual to be re-identified because it's a unique record in the data set. But in reality, it's actually not that simple, because if the background knowledge that is available to the attacker about the population looks like this, then you can see that there are 2 individuals actually in the population that would match this specific record. So it's basically a combination of the information about membership of a certain individual in a data set and then combined with a linkage attack. And you first need to be quite sure of membership before you can do sort of a linkage attack. So sort of to give you an idea of the why risks might sometimes actually be lower. But the problem, of course, is that typically you don't know much about the population, and it's pretty hard to get good estimates on this. Still, there are a few models that have been suggested, particularly even in, as I said, in the statistics community, for sort of estimating properties of the population from the data set that you're having at hand, so from your sample, and when you know that there's a random sampling process that has to be done. And there are also a few of these methods that are basically supported in the software that we have implemented. And but what you, of course, always also can do is if the data set that you're planning to publish is a subset of a larger data set, and you also have access to the larger data set. So let's assume, again, an example from the medical context. You have whatever, a hospital information system, and you have a database, and you want to hand out information about patients having a certain diagnosis, then you know that they're actually a part of this larger database. And then what you can do is you can simply assume that your larger database represents the population, which gives you more exact risk estimates that are still conservative. So this is for a way that this can be approached, but as I said before, quite often it's nothing is really known about the population, and not enough is known about the sampling process, or it's extremely skewed, which then sort of makes this infeasible. So I already mentioned differential privacy, and this is a slide on it. It's a very nice visualization. There's also a link below here. It goes to the blog of the author of this drawing. It's an extremely good blog. If you're interested in the topic, I can really just recommend reading this. What is interesting about differential privacy, which, as I mentioned, is basically really considered the gold standard nowadays in data anonymization, but let's say privacy protection or privacy enhancing technologies, also implemented by quite a lot of companies in certain contexts, by Apple, for example, but also by Google in some contexts within the Chrome browser. What this basically does is it sort of accepts that the idea of having anonymity to be a property of a data set doesn't really work. So the idea is, let's not have anonymity as a property of a data set, but let's have anonymity of a property of a processing method. It's a method in which you process data that actually provides you the guarantee. It's not the data itself. And how does this work? This basically works the following way. You do have a randomized process in which you process your data, and processing can mean anything. Processing can mean doing a database query and getting some counts back. And processing can mean doing statistical analyses and receiving some sort of results, but processing can also mean having an input data set and generate an output data set, so sort of a more typical anonymization process. And now you make this processing method randomized, and then you sort of make sure that it fulfills the property that when for each and every data set that you can basically think of. So this is sort of an analytical process. You have to prove this mathematically for your method. For each and every data set that you can think of, and the same data set with any individual removed, you basically get the same result out of your processing method. So and this basically gives individuals plausible deniability, because from the data, and in the end it's the data that you hand out, you can never know whether or not any specific individual has been sort of part of the data set that has been processed. And this sort of gives the whole thing a new perspective. It's interesting, again, if we think back about the GDPR and how the GDPR defines anonymity as more a property of a data set and not as a property that has anything to do with the process, how this needs to be interpreted from a legal perspective. But at least in theory, it's a model that can give you a very, very high degree of protection. There are a few pros and cons. And the pros are really, or the advantages are actually really big. There's basically no need to make assumptions about attacks. In the other models, you often have to think about what could the adversary know, which variables might be available to the attacker. Doesn't really care, it doesn't really matter at all in this situation. And you can map this down to sort of being a protection from membership attacks. And if you think back to sort of the pyramid, then membership can be seen sort of as the root of all evil. As long as you're not even able to decide whether a certain individual is contained in a data set or not, you're basically also not able to perform any other types of attacks. And membership is exactly where this model basically, model basically protects individuals from membership disclosure. And you can also do things such as compositions or combining many differentially private processes with each other and so forth. There's also this post-processing guarantee. So whenever you have a differentially private output, you can do whatever you want, but basically whatever you want with it without losing any of the guarantees that you already have. But there's of course also problems associated with this. And maybe an interesting point here, I think it's the current US Census has decided for the first time ever to not use the traditional statistical methods that are typically using, but really to use differential privacy for protecting the tables and the statistics that are being released as a result of the census. And there have been really fierce and huge discussions in the community about whether or not this is a good idea. And this has to do with the fact that also differential privacy has the exact same inherent risk-utility trade-off. So the more you protect data, the more you lose usefulness. And this is typically done by adding noise. And there has been lots of discussions in the community about whether or not this will work for the US Census data set or not. We will see how it turns out. And but there's also in medicine sometimes a problem gives you the challenge that the mechanism is basically not truthful. So it means there's random noise added to your data, which can be a problem in some contexts. And it's also not quite intuitive. So it's really hard to communicate to others. Again, I have an example from medicine to ethics committees, for example. The idea of k-anonymity is very easy to communicate. You just say, yeah, we make sure that there's no individual in the data set. There are only groups of individuals. Okay, makes sense. But to really explain what differential privacy means, it's a very subtle mathematical guarantee of a randomized algorithm. This is something that is really not that easy to understand. And there's also a privacy parameter, which is called epsilon. So it's sort of comparable to K and k-anonymity. And also there it's quite difficult to to really understand what different values of epsilon sort of have, what the different implications are. But this can, and that's what this figure is showing, can be mapped to sort of guarantees on the suspicion that adversaries can have when trying to determine membership of individuals, which sort of gives you an intuitive understanding of what epsilon means in epsilon differential privacy. Now, part 3 would be sort of talking about the anonymization of analysis results, starting again by a look into the GDPR. And the interesting thing here is recital 162 in this case, as an example, shows that the GDPR also says that the results of analysis must be protected, which of course intuitively makes sense. And whenever data is processed for statistical purposes, and statistical purposes, of course, also includes scientific research. And the statistical purpose, which is one of the legal basis, I think, under which you can process data under the GDPR, but it also assumes that the result of such processing is basically not personal data anymore, but it's aggregated data, and aggregate data is sort of also supposed to be anonymous data. And as I mentioned before, even this can be hard to achieve. In the following slides, I have an example on machine learning. Machine learning is also one of the areas where this can really be a problem, and where so there are techniques such as federated learning, for example, that are often being mentioned as a solution to the problem of having a hard time anonymizing data and sharing it. So the idea, you sort of bring algorithms to the data, and you train, for example, individual machine learning models at the different sites, and then create an ensemble of the resulting methods. So different approaches that these can help to overcome challenges with data anonymization and make it easier to share data. But also there are actually quite a lot of challenges involved, because you never know what information is actually encoded in let's say non-trivial machine learning models. There are some works that show that it's really simple or relatively easy to, for example, protect logistic regression models. But today, of course, it's all about deep learning and about neural networks, and there this can really be challenging to make sure that it's actually not personal data that is being encoded into these models that you are training, and that there are no ways for sort of getting this personal data back out of these models. And I will skip this a little bit. So just to sort of give you an idea, there are ways of doing membership attacks if you have machine learning models, where you can sort of, with a very high accuracy in some circumstances, determine whether or not data about a specific individual was actually part of the data set that was used to train a model. But you could also do things such as deriving attributes by, for example, trying different combinations of features and feeding them into the model, and see what the prediction model predicts. And when you know what needs to be, or what is the correct prediction, then you can sort of derive information on the features that you did not know previously. So this again can be correlated to this pyramid that I showed, sort of a form of attribute disclosure. And of course, coming back to the topic of texts, for example, when we are processing textual data with deep learning models, there are also examples that show that it's really sort of tokens of the text, different parts of the text can be encoded into the resulting models, and there might be means to extract them. And let me give you here an example. This is exactly the same slide that I just showed on differential privacy. Of course, differential privacy has also been implemented in many machine learning models. For example, TensorFlow does offer a differential privacy implementation. But as I mentioned before, there are the same in sort of inherent risk and utility trade-offs that come when you anonymize data. They also come when you use differential privacy, and for example, when you integrate differential privacy into a training method. So you could do this, you have a randomized training mechanism, and you basically just have this guarantee that if I remove a specific individual or edit, it's basically the same model that will come out of my training process. This is doable, but this again provides you with trade-offs that need to be taken, exactly this risk-utility trade-off. And there's quite an interesting paper, again, it's an example from the medical domain, that applied this to sort of a machine learning model for personalized warfarin dosing. So it's a blood thinner basically that is being used to treat patients in certain contexts. And they were basically able to show if you try to or if you create a privacy preserving model for predicting the correct dosage for a certain individual, and then you have this privacy parameter epsilon from the differential privacy model. And basically when you decrease epsilon, because with epsilon it's other than with k-anonymity, when you increase k, the protection becomes stronger. With epsilon differential privacy, it's exactly the opposite. The smaller you make epsilon, the fewer differences you can expect, and basically the higher the protection is. And they basically showed that the smaller you make epsilon, you will get a higher degree of protection. So there's more protection from disclosure, but of course your predicted warfarin doses become increasingly less optimal, basically putting patients at risk of dying. So this is sort of a thought experiment, but as really a practical application sort of in an example, but really showing what this can mean in practice, for example, if you use such models to treat patients. Okay, ARX, as I mentioned before, is a tool developed by my group. It focuses on tabular data, and I would argue that it's in the area of tabular data, at least, it's probably the most comprehensive tool that you will be able to find, and combines a lot of different approaches. So traditional things such as k-anonymity and many, many more of these hundreds of models that have been suggested, but also differential privacy. You can do privacy preserving machine learning, so sort of try to create machine learning models while making sure that certain privacy guarantees such as differential privacy hold. And it's also quite scalable, so there have been practical applications to data sets with billions of records. And an interesting point is that it does have a quite comprehensive also graphical user interface. So when you want to use the software for really practically anonymizing data, you would typically do this via a programming library that we provide, because you need to really be able to flexibly combine different techniques, which is hard to do through a graphical user interface. But the UI gives you sort of limited access to all the different features that are available, which makes it quite interesting for training purposes. And this is a picture here from Korea, the Korea Internet Security Agency that basically did training with members of, I'm not sure whether probably external people that could register for this workshop. So quite a lot of workshops that are being done all over the world to sort of train people with anonymization techniques, or at least to sort of provide some initial experience, because I think that's quite obvious. It's a really complex topic, and you really need to know what you're doing to be able to do this in practice. But it has also been used really to create open data sets that are available on the internet. As said, this is dangerous, so these are quite limited data sets that can be downloaded publicly, and that are also been used actually in many different domains. We developed it coming from a healthcare context, but for example, telecommunication providers have used the tool quite extensively, or the software quite extensively, to anonymize the location traces and all those types of information that they have, and to sort of monetize it. There are health insurances that have used this to anonymize quite large databases. And also a specific property of the software, we have quite an industry-friendly license, Apache 2, and there are actually quite a lot of commercial software tools that you will be able to find on the internet that have integrated the software to provide certain anonymization features. And what also makes me a little proud is SAP with the HANA in-memory database. They do have a data anonymization module where they have not integrated our software, but actually one of the core algorithms that we have developed for the software. And this is all published, so it's scientific work, it's scalable and mature software, but at the same time, we are publishing papers about how we are developing this and how we have made it that scalable, because that's really one of the unique selling points, many different anonymization techniques, and they can all sort of be used together and combined in a flexible way. This makes the software quite unique and also quite successful. I would say anonymization software is more of a niche product, but in the last 7 years, it has been downloaded more than 50,000 times. So how does it look? This is sort of an overview of the UI, which also gives you an impression of the different types of methods that are supported. Should not be surprising after listening to me for an hour now that there are basically 4 different perspectives. There's a configuration perspective where you can load data and specify your anonymization process. For example, if you have assumptions or you know something about what might go wrong, can enter information about the population, how you want to measure risks, how you want to measure utility, how data might be transformed. You can configure all those various types of things, and then you can hit a button and the software will sort of do an automated optimization and anonymization process, and then provide you with 2 perspectives for analyzing sort of the usefulness of the data, the utility, sort of try to figure out how statistical properties have changed, for example, but also to do a risk analysis, so sort of taking a look at residual risks. As I mentioned, risks can never be reduced to completely zero, and here you can sort of take a look at how risks have changed and how effective your anonymization process was. And there's also an exploration perspective, because there's not just one perfect solution to an anonymization problem, but there are typically many different solutions, many ways this could be done, and the software might not be perfect in selecting the best one for you. So it also gives you ways to sort of try to find a solution that might better fit your requirements than what is sort of suggested automatically. So I will again speed up a little bit and maybe come to my last part here, real-world examples, which I think would be a good way to sort of wrap this up. Again, as an example, coming from the perspective of ARX, we recently applied this to a large data set from a COVID-19 registry, and I will talk a little bit about this. We can also see here, this is sort of also gives you an idea of the practical implementations, that there's a range of official guidelines and reports mentioning ARX, so from the European Medicines Agency or the European Union Agency for Network and Information Security. Ministries from various European countries have published reports that mention the software, which again sort of shows a little bit that there's actually not so much around, I would say, right? Data anonymization is a challenging problem, and there are just not so many tools available. Now, I mentioned this COVID-19 data set, which we anonymized just a few months ago as part of our sort of work in the context of the COVID-19 pandemic. This was in the context of LIOS, which is a larger European registry that basically captures data on the clinical course of SARS-CoV-2 infected patients, and they sort of follow an open science approach and wanted to make it relatively easy to provide data to the public, but also to researchers. And we supported them by sort of developing 2 different types of data sets. We developed a public use file. This is the data set which is really available through the internet. So it's highly protected by different anonymization processes. But again, that sort of also shows you this inherent risk-utility trade-off. It consists of 16 variables only. So it's more of a sort of an advertisement idea, sort of also gives citizens the possibility to take a sort of a little peek into the data. But of course, if you want to answer scientific questions, more complex scientific questions, you need more data. That's why we created a second data set sort of based on the anonymization methods developed for the public use file, which contains more than 600 variables, and then combines this highly formal and strong and strict approach that we apply to the public use file, that combines this with different additional rules of thumb, more or less. So not that strict, because when you have a dimensionality, is a very high dimensionality is a very bad thing when you want to do anonymization. With k-anonymity, it's obvious. If you have 600 variables, there will be no way of making sure that each record is indistinguishable from, let's say, for example, 5 others regarding all those 600 different variables without deleting all information from the data set. But it's actually the same is true also for differential privacy to some degree. So dimensionality is always a problem. That's why we combined for the scientific use file those very formal approaches with more rules of thumb approaches, I would say, and then created a secure environment in which this data set is being shared. So you have to request access to the data set through a formal process that is then being checked by a committee. You need to sign a contract. There are some obligations to how you need to handle the data to make sure that nothing goes wrong. This sort of also shows you this gives an insight into how such multi-layer approaches can work. Now, this pipeline for the public use file has been, for both files, has been built with ARX. And what is also interesting here is that we did this without ever seeing the data. So, and this can also be done. It's of course a little bit complex, but in this case, there was no legal basis for us seeing the data from the registry. So what basically happened is that in Cologne, they created a random data set, which just gave us no real statistical information encoded, but gave us a little bit an idea about the attributes and the domains that they have. And we then developed this anonymization process and packed it into code, and this code was shipped to Cologne, or switching automatically, and they executed it on the data set, and then they generated a report, and then the report was sent to us, and then we updated the pipeline, and we did this like 7 times over several weeks until we came up really with an anonymization process that is really strong, but at the same time also provides high utility for this restricted 16 attribute data set. And another key message, if you really want to do this, and what we also here did is you need to sort of combine quantitative approaches and qualitative approaches. So I talked a lot about quantitative approaches now, doing things such as k-anonymity, having mathematical or statistical models, but you can of course also follow a qualitative approach and sort of try to document a subjective feeling that you have about the data, basically. And there are also methodologies that you can follow when doing that. And in my perspective, it's a good idea to sort of combine both approaches with each other. So, for example, if you reason about what the attacker might know, what potential background knowledge could be, what context information is potentially relevant, you can do this from a qualitative perspective to sort of, for example, come up with risky variables, and then have a quantitative, more formal mathematical process follow that sort of protects the variables that you have selected to this through this qualitative process. And again, here it starts to become a little bit difficult. How do you translate legal requirements into technical options, basically? And there's one document also relatively well known in the field. That's the opinion on anonymization techniques by the Article 29 Data Protection Working Party, which today is the European Data Protection Board. And they sort of thought a little bit about anonymization and basically defined 3 threats from which you should protect data, singling out linkability and inference. And there are mathematical models that you can use to address these 3 different sort of types of threats. These models are also supported in ARX, and that's why we basically use those models to protect the data set. They're also coming back to this question: what is an acceptable risk threshold? It's quite an interesting story, but there's sort of a very short answer: 0.09. And so basically 11, if you think about k-anonymity, k equals 11, and this there's no real legal reason for believing that there is a good risk threshold. There's also no good technical reason for believing that this is a good risk threshold, but it is a risk threshold that is quite frequently used and has initially been suggested in some US documents and then took its way to other documents and guidelines and is frequently mentioned, but there's actually no real reason. But there's quite a lot of literature that you could refer to when you want to justify why you have selected a certain risk threshold. It's a good idea to use 0.09 because there's quite a lot of justification for this, or there are quite a lot of references for this basically in the literature. Yeah, and we implemented this in this case with quite traditional methods using k-anonymity and t-closeness, and then also continuously monitored what actually happened to the data. Oh, there's another very interesting point here to mention. In LEOS, the data is published sort of as a continuous data stream, this public data set. And so the data set is not just published once, but it's published multiple times. And that's, again, something that is not uncommon and that comes with additional challenges when you anonymize data, because you have to be very, very careful to do a certain process that when data is being updated and you release it several times or share it with someone several times, that it's not possible to sort of intersect the different data sets with each other and in this way sort of gain insight into additional information that you actually wanted to hide from the recipient. So, and in this case, there was a special process implemented for making sure that this doesn't happen. We basically sort of keep records back as long as they are too risky to release, and then at a certain point release them. And there's not a lot of dynamic transformation of the data being done, but it's basically a relatively static, predefined scheme. And then, as I said, the protection is actually done by holding records back that do not fulfill the privacy criteria that we have specified. And that's the data set, as I said, 16 different attributes. You can see here the typical demographic properties, age, gender. There's a little bit information on time, so when COVID-19 was first, or the SARS-CoV-2 infection was first diagnosed, a little bit of information on the medical course and on treatment, and then also a last known patient status. So more of a table summarizing everything that is being available through this registry. But even anonymizing such a relatively easy file in a relatively simple file in a really strong manner can actually be quite challenging and time consuming. And this will be sort of my last two slides. We then also studied how this anonymization process basically has impacted the statistical properties. And here, these are models that we use that work on this principle of hiding in the crowd, and this leads to a somewhat counterintuitive property, because the more individuals you have included in a data set that you are protecting this way, actually the easier it becomes to protect those individuals, and the less information has to be removed to achieve a certain degree of protection that you need to achieve. And this can also be seen in the data set as the data that was available in the registry sort of grew over time. In the beginning, we needed to hold back sort of 40% of the records in the registry, and then this really quickly increased. And currently, in this public data set, it's almost all records that are being published. You can see a very tiny fraction here that is being held back because it does have very special combinations of attributes, and they are really sort of too distinguishable from the remaining records. And if you calculate some statistics, such as, for example, the case fatality rate, you can see here that in the beginning there was quite a huge difference between the statistics calculated on the original data set in the registry versus the data that is being released to the public. But currently you can see that those statistics are really very, very close to each other, almost indistinguishable. And in summary, we really believe that in this case, it has a really negligible impact on data utility, which you can also see here in the descriptive statistics about the data set, the distribution of individual values. You can see that there are a few very, very, very minor differences between the two data sets, but it's really manageable, I would say. Okay, so in summary, going back to this result, this application example, basically, the overall approach was really to very, very context specific. One of the key messages depends on the types of data you have, on the scenario in which you want to publish it. You have to develop something that applies specifically to this. This is time consuming, and this requires efforts and expertise. Typically, you will need multiple layers of safeguards, so you could do qualitative in combination with quantitative anonymization processes. You might want to create secure and safe environments for making data accessible to others. And you, of course, should try to really rely on recommendations from laws and guidelines. But at the same time, there is, unfortunately, at least in my experience, quite a lot of legal uncertainty involved in anonymization at the moment, at least in the European Union. And it's quite hard to sort of come up with an approach that will really be where you can be pretty sure that this will be accepted, for example, by supervisory authorities. And also, as a result, I think what is very, very important is that what is being done in a transparent manner, that you create thorough documentation, which really explains your reasoning behind what you are doing. Why do you think that certain attributes, for example, need to be protected? Why do you think that certain attributes do not need to be protected? What are the assumptions that you are making? You should try to document all this. You might also be aware of in the GDPR, what is required nowadays quite often is the so-called data protection impact assessment, also including a risk analysis. And sort of create something like that also for your anonymization process. Yeah, that would be sort of my most important recommendations should you want to engage in this interesting journey of applying anonymization in practice. And at this point, I would thank you for your attention, and I'm really happy to answer any questions that you might have.